All right. Chapter 6, question 9. So the question says, which set of three quantum numbers, n, l, and m sub l, correspond to a 3p orbital? All right. So to answer this question, we need to remember what the 3p refers to when we talk about a 3p orbital. So 3p, the 3 is the first quantum number. So when you're talking about an electron configuration, 3 is the first quantum number. Our quantum numbers are n, l, m sub l, and then m sub s is also a quantum number at the end. But here we're only given the n, l, and m sub l of quantum numbers for some electron somewhere. Alright, well, if it's a 3p orbital, then 3 indicates to us the quantum number n. So our n value should be 3. And that's what is provided for us for all of the answers. 3 is the first choice. So the L value, what will L value be? Well, L always can be, n can be equal to 0, 1, 2, no, sorry, starting over. N can equal to 1, 2, 3, 4, 5, etc., all the way up to, well, theoretically infinity, but it's usually about 7. Now that n value also corresponds to the row in the periodic table. So the first row, hydrogen and helium, have an n value of 1. The second row, starting with lithium, going all the way across, have an n value of 2, and so forth. Right? The third row, the fourth row. Those are our n values. L is an indication, that value there, an indication to the block on the periodic table where it's at. So we have our first two rows in the periodic table. Let me sketch a little periodic table here. Here are our first two rows or first two columns in the periodic table. Then we have our transition metals, our block across there. And then we have our non-metals. There's our staircase in here as well, right? Our halogens and our noble gases are here, right? Well, the L value corresponds to whether it's in this block, this block, this block. Then down below there's also what's called the intertransition metals. All right, there's an L value that corresponds to this one as well. L value for 0, this is L equals 1, this is L equals 2, and that's L equals 3. There we go. So L can either be, if n equals 1, L can either be a value 1 less than n, and then counting up, or counting down. So when n equals 1, L, the only choice is 0. If n equals 2, L can equal, again, 1 less than n, so that would be 1, and then counting down to 0. So if n equals 2, L can equal 1, or it could be 0. If n equals 3, L can equal 1 less than n, 2, and counting down, 1, or it can equal 0. Alright? So when n equals 4, L can equal 3, 2, 1, or 0. Alright. So when we look at the possible numbers for us, one of them might be 3, because we saw that we're looking for the 3p orbital. So the 3 is the n value. The p helps us identify which block we're in. These blocks are also called the S block. This is the S block. This is the P block. This is the D block. And this is the F block. Alright? So, when L equals P, or when we are in a P orbital, that is L equaling to 1. L equals 1, because this is the P block. Alright? So when n equals 3, L can either equal 0, 1, or 2, right? 0 meaning here, 1 meaning here, or 2 meaning here. So this corresponds to n equals 3, L equals 1, and m sub L. What could m sub L equal to? Well, m sub L is equal to, it can go as high as the L value and as low as the negative L value. So let's say I have an n value of n equals 3, L equals 1, and m sub L. What could m sub L be if L equaled 1? If L equaled 1, what we said, m sub L could be as high as 1 and as low as negative 1 and all the integers in between. So that's 1, 0, and negative 1. If I had a scenario where I was looking for n equals 3, L equals 2, m sub L could now be either 2 or all the way down to negative 2 and all the integers in between. So 1, 0, negative 1, and negative 2. Alright, so that means that which set of 3 quantum numbers n, L, m sub L corresponds to a 3p orbital. So the 3 is our n, the p block is over here, so L equals 1, and then the m sub L, if L equals 1, m sub L could equal to either negative 1, 0, or minus 1. And if we look on there, we see that we only have one option there that will fit for us. Well, I mean, it might vary depending on your problem that you're answering there. Okay. Let's go to the next problem. In the next problem, this is problem 6.51. Part A, for n equals 4, what are the possible values of L? Alright, well, we talked about this already just a second ago. If n equals 4, L, possible values of L are, we can always have 0, and then it counts up higher, but it always has to be up to 1 minus L. Another thing about the L values, the number of possible L values is always equal to the n value. So the number of possible L values here is 4 because n equals 4. So the values can be 0, 1, 2, or 3. There's 4 possible values because n equals 4. L value can never equal n. Alright? So if n equals 4, L can be either one of those values. For part B, if L equals 2, what are the possible m sub L values? So if I have a scenario in which L equals 2, what can m sub L equal? Well, m sub L can always equal whatever L is, or it could equal all the way down to a negative L. And it can equal anything in between. So 2, 1, any integer in between, negative 1 or negative 2. So if L equals 2, those are the possible m sub L values. Alright, if m sub L equals 2, what are the possible values for L? So if m sub L equals 2, what are the possible values for L? Well, L had to be at least 2, right? It could be 2 or higher. For all atoms in their ground state that are known to exist. So, if L equaled 2, has to at least be 2, that 2, what does that 2 correspond to? I'm drawing the periodic table again. This is L equals 0. This is L equals 1. This is L equals 2. And then the inner transition metals down here is L equals 3. So, if M sub L equal 2, L could be equal to 2, or it could be equal to 3. Alright? So, we talked about how theoretically you could have much larger values, but they limit us for all atoms in their ground state that are known to exist. So these are in their ground state, meaning not excited electrons. Alright? So that's 651. Problem 654. Given the values for n, L, and m sub L for each orbital in the 2p subshell. Enter your answer. Give the values for n, L, and m sub L for each orbital in the 2p subshell. So 2p. The p shell, the p orbitals are the orbitals that fill when you fill the p block. Alright? And in the p block, we have 1, 2, 3, 4, 5, and then 6 elements going across the p block here. 1, 2, 3, 4, 5, 6 elements. We have our transition metals here, and then we have our alkali and alkaline earth metals, right? So again, this is the S block, this is the P block, this is the D block, and then down here is our F block. Alright? So if we're talking about a 2p orbital, this is hydrogen here, this is helium here, and that is our top row, right? Our top column, sorry. And then our second column. If n equals 2, and that's what it says, a 2p subshell. So that first letter there tells me that I'm in the second row here. If n equals 2, then I'm in this row. If I'm talking about electrons in the p orbital, this is the p block over here. So n equals 2, these are the electrons which are adding in to the p orbital. So it says give the values of n, L, and m sub L for each orbital in the 2p subshell. Alright? So, for n equals 2, and L being referring to the p block, that means L equals 1. So again, S is L equals 0, P is L equals 1, D is L equals 2, and F is L equals 3. Alright? So, given that we're 2p, n equals 2, L has to be equal to, it can be either equal to 0 or to 1, and in this case L equals 1. So, we need to give the value for m sub L as well, and for, let's see, give the values of n, L, and m sub L. So this is n, L, and m sub L for each orbital in the 2p subshell. Well, each orbital can contain 2 electrons. That's the rules of orbitals. All orbitals, any kind of orbital, will be able to contain 2 electrons. And because we have 1, 2, 3, 4, 5, 6 elements across this p block here, across this little section, we're going to need 3 orbitals, because each orbital can contain 2. And the p orbitals look something like this. And we call them dumbbells. There's one in the x-axis, one in the y-axis, and then one third dimension coming out at us in the z-axis. Each one contains 2 electrons. For each of these, m sub L, so this is n, second row, L, one of these p blocks, and m sub L refers to -1, 0, and a +1. Now, those ones are degenerate, so it doesn't matter which one you're referring to. But those are the three possible m sub l's. So, the possibilities are going to be n equals 2, l equals 1, m sub l equals, it can be equal 1, n equals 2, l equals 1, m sub l can be equal to 0. And the last one would be n equals 2, l equals 1, m sub l equals negative 1. So those are the three possible sets of n, l, and m sub l. Alright, give the values, part B, give the values for n, l, and m sub l for each of the orbitals in the 5D subshell. 5D. Okay. So, if we're in 5D, the n value, what's the n value for 5D? Well, the n value for 5D is going to be what? Well, if it's 5D, that first letter is the n value, right? So it's going to be 5. So n equals 5. And that means in the fifth row. 1, 2, 3, 4, 5, right? So we count down to the fifth row. L. What is L going to be equal to? Well, L is either equal to, with n equals 5, L can be equal to 0, it can be equal to 1, it can be equal to 2, 3, or 4, right? L is always, the most it can be is 1 less than n. And it counts from 0 up to that value, or from that value down to 0, however you want to think about it. Alright, so if we're talking about the 3D, this is the D block here, and L equals 2 for that. So n equals 5, L equals 2. Now m sub L. What can m sub L be equal to? Well, you can have m sub L being equal to, at the most, L, and at the least, all the way down to negative L. Alright? So, one set would be m sub L equaling 2. One set would be 5, 2, and m sub L equaling 1. Then you could have 5, 2, and m sub L equaling 0, 5, 2, m sub L equaling negative 1, and 5, 2, m sub L equaling negative 2. So there would be 1, 2, 3, 4, 5 sets of these numbers. Again, 5, 2, 2, or 5, 2, 1, 5, 2, 0, 5, 2, negative 1, 5, 2, negative 2. Alright. So, $6.55. Which of the following represents impossible combinations of n and l? Alright? So n being the first letter there. Alright, so we have either 4, 5, 2, or 1. 1, 2, 3, 4, 5, right, in the first column there. And if n equals 1, for example, L has to be what? What are the possible L's? Well, L has to be 0. And if you remember, 0 corresponds to our S block, right? So this is the S block, and that's where L equals 0. Our P block over here is L equals 1. Our D block, L equals 2. And our F block down here, L equals 3. So if n equals 1, L can only be 0. If n equals 2, so that means L equals 0, you can only have an S. Or an S, that's the S. So you could only have one S. You couldn't have one with a P, a D, or an L. How about 4? If n equals 4, on the other hand, then L could equal 0, 1, 2, or 3. Again, if n equals, whatever n equals, that's how many L values are possible. Okay? So, if n equals 4, L could equal 0, 1, 2, or 3. if n equals 5, L could equal, and so 0, 1, 2, or 3 would be either the S, P, D, or the L. Alright? If n equals 5, then L could equal 0, 1, 2, 3, or L could also equal to 4, theoretically. Alright. So, let's see, did we get that right? Alright. But we see that it's impossible to have something, for example, saying 1p, right? Okay, so 656. Alright, for the table below, write which orbital goes with the quantum numbers. And it says don't worry about the x, y, or z subscripts on the m sub l. If the quantum numbers are not allowed, write not allowed. For the table below, write which orbital goes with the quantum numbers. So, for example, if n equals 1, and L equals 0, and m sub L equals 0, then that n equals 1 is the first row, L equals 0, and L can equal 0, 1, 2, 3, 4, right? And this is S, P, D, F, G, alright? So, if L equals, where are we at? No, if n equals 1, L can equal to 0, and if m sub L equal to 0, that is our S orbital, and that is going to be n equals 1, so it's a 1s. And n equals 1, that's 1, and if it's 0 here, it's 1s. When n equals 3, n equals 3, leave that up here just a second, S, P, D, F, 0, 1, 2, 3. Alright, when n equals 3, L has to be either 0, 1, or 2, but it can't be -3, so that one's not allowed. If n equals 3, we can have L equaling to 2, that's okay. And if L equals to 2, we can have, that means that has a 3D. So L equals 2, so 3D orbital. Alright. Let's see. And m sub L can be equal to -2 if our L value equals to 2. Alright. If n equals 2, then that is a 2, and L equals 0, that's the S size, so that's a 2s orbital. If L equals 0, well, the problem there is m sub L can only be either as high as positive L and as low as negative L. But if L is equal to 0, then m sub L has to be at least the most 0. So that is not an allowable quantum number. Neither is 0, 0, 0, because 0, you're never going to have an n value of 0. 421, when n equals 4, that's 4, 2, a 4d orbital, that's alright. And 1 is an m sub L value, that is fine, because if L equals 2, then m sub L can either be -2, -1, 0, 1, or 2. Right? Okay, 5, if n equals 5, and 3 is F, so the 5F orbital, that's the one that's referred to on the bottom, and that m sub L value is fine. Okay, so those are quick question answers that we're looking for there. Go ahead to chapter 6, question 10. How many p orbitals are occupied in a sodium atom? Well, in a sodium atom, we have how many p orbitals are occupied in a sodium atom. In a sodium atom, if I remember right, we have 11 electrons, right? 11 electrons, and you can look at the periodic table and see how, the sodium atom goes up to, the first 2 electrons go into the 1s. There's 2 electrons in the 1s. The next 2 electrons go into the 2s, and there's 2 of them. So I'll write up here again. Sodium has 11 electrons. 2 of them are in the first 1s. 2 of them are in the next 2s. And then we have the 2p. And the 2p can hold up to 6 electrons. Again, the p orbitals look like this. One of them looks like that. It holds 2 electrons. You can think of them as being different lobes if you want. The second p holds 2 electrons as well, and the third one comes down in front here and behind, and it holds 2 electrons as well. So that's a total of 6 electrons that can be held there. 6, 7, 8, 9, 10. And then the 11th electron goes into the 3s. So how many p orbitals are occupied in the sodium atom? Well, there's 6 electrons in the 2p, and there's 1, 2, 3 orbitals. 3 orbitals that are occupied. So, what is the only possible value of m sub L for an electron in the s orbital? M sub L. So this is quantum number rules. What is the only possible value of m sub L for an electron in an s orbital? Well, if I have an s orbital, that means my L value has to equal 0. So I don't know if you remember, but S, P, D, F, and L equals 0, 1, 2, and 3. So if L equals 0, what are the possible m values for S equals, so if L equals 0, that's what for S. And m sub L has to be equal to 0 too, because m sub L, whatever the m sub L value is, can only be as high as the L value and as low as the negative L value. So if it's 0, then m sub L has to be equal to 0 also. Part B. What are the possible values of m sub L for an electron in the d orbitals? S, P, D, F, 0, 1, 2, 3. These are the L values for these sections on the periodic table. If I'm in the d orbital, then L equals to 2. Therefore, m sub L can equal to either -2, -1, 0, 1, or 2. Part C. Which of the following quantum numbers are possible for an electron in an atom? So now we're introducing the fourth quantum number, which is m sub s. M sub s can either be +1/2 or -1/2. So I look at all the n values, and I know that all of the L values have to be 1 less than n, and that all the n values have to be greater than 0. So the second one, -2 for n value, won't work. Okay. Starting up with part C on learning the quantum number rules. If n, whatever n equals, m sub L, or L, always has to be 1 less than n. So L and n can't be equal to each other. So the first one, 3, 3 for n and L, that's not a possible combination. Also, n can never be a negative number. But the rest of them, so the first two don't make any sense, but the rest of them could be okay. L always has to be at least one value, one integer lower than the n value. That m sub L. M sub L is always a positive number, so -3 there on the fourth one down won't work. M sub L could be 0, that's fine. If L is 2, M sub L could be -2, -1, 0, 1, or 2. So there's the second to the bottom. The L value is larger than or the M sub L value is larger than the L. That can't be. Everything else is okay. So again, no negative quantum numbers except for the last one. It can be either +1/2 or -1/2. Not -1, so that's not a possible quantum number. So that is how you do C there. Alright. Chapter 6, question 7. The ground state electron configuration of scandium. Alright, so what is the ground state electron configuration of scandium? Well, you can look at the periodic table. You can look at the periodic table there too. Ground state electron configuration of scandium. So 21 electrons, scandium looks like this. 1s, 2, 2s, 2, 2p, 6. There's 6, 7, 8, 9, 10 electrons there. We have to get up to 21 electrons. 10, and then 2p, 3s, 2, 3p, 6. So we have 2, 10, 16, 17, 18, 19, 20, 21. So we need 3 more electrons. 3p6, 4s2, 3d1. Is that in the right spot for scandium? So for scandium, you can see that it's in the D block. And it has 1 electron in the D block, so that doesn't make sense. So that's the electron configuration for scandium. Alright, the last one in this section. Chapter 6, question 11. The element that corresponds to the electron configuration 1s2, 2s1 is what? Well, 1s2 means 2 electrons in the 1s. 2s1 is only 1 electron in the 2. So that's got to be, if you look at your periodic table, first of all, it tells you it has 1, 2, 3 electrons. So that's a good way to identify what it is. Second of all, if you follow the periodic table, you have hydrogen on the right, and then you have helium on the left. There's 1 in the 1s, 1 in the second one in the 1s, and then the next one goes into the 2s1. And that's lovely. Alright, thanks for watching.